You all, Daryl Lee Berry Jr. back. Going to do some more thermodynamics problems. We'll continue from where we left off earlier with the last few problems in this particular assignment. And maybe I'll come back tomorrow for more. So we left off on problem 120, no, 123. So let's see what will be the next problem. So we have four more problems, 134, 35, 36, and 38. So let's get through these. 134, A through C. We have an ideal diatomic gas in a cylinder with a movable piston undergoes a rectangular cyclic process shown in figure 110b. So we have a cylinder and we could imagine a piston up inside the cylinder like so. Pushing on the air. An ideal diatomic gas, let's say N2, is floating in there. Movable piston. Assuming that the temperature is always such that rotational degrees of freedom are active, but vibrational modes are frozen. So that means that it only has 6 to 8. So sometimes these are considered vibrational together. So I would say 6 degrees of freedom. Also assume that the only type of work done on the gas is quasi-static compression expansion work. So quasi-static is internal equilibrium to the system. It could be isothermic or adiabatic. So quasi-static is internal equilibrium. So there's internal equilibrium. For each of the 4 steps A through D, compute the work done on the gas, the heat added to the gas, and the change in the energy content of the gas. Express all answers in terms of P1, P2, V1, and V2. And the hint is compute the change in U, the change in energy before Q, using the ideal gas law and Egger partition theorem. Let's see what they did for this one. Right? So it says it's easiest to first compute the work done during each step using work equals negative P change in V, which is one I don't think I have on the formula sheet. It's not. Work equals negative P change in V. Good. I know I have the force one here. Force equals PA. And also work equals negative P change in V. That for steps A and C, there is no work done because the volume doesn't change, right? So, yep, so A, the volume, the vertical stays on the same volume 1, so the volume doesn't change. All right, so let's actually go through these. So A through C equals C change in V equals negative pressure actually changes. This for steps A and C. Negative P0 equals 0, so work is 0 for A to C. Work is 0 for, for A and C. For steps B and D, the pressure is constant, so we don't need to set up an integral. So for instance, the B work equals negative P change in V equals negative P2, and velocity changes from V1 to V2, so that's V2 minus V1. B work equals negative P change in V equals negative P1 V1 is V2, which is the same thing as P1 V2 minus V1 with a positive. So each molecule has 5 degrees of freedom. The thermal energy of the gas at any point is U. It says 5 degrees of freedom for this. I would have said 6. Oh, that's what it is. I was looking at H2O. This is the ideal diatomic gas. So let me put this monatomic, diatomic, and I don't know what to call this one. I'll just call it complex. So this is a diatomic gas. The vibrational is frozen out. So we have just kinetic or translational and rotational. So that's 5. Thermal energy of the gas at any point is U. This is the one I'm looking for. Be sure this is for a specific problem. So I'll keep this one here, but I'll keep it just in case. Just put a question mark on it. So we're using this one, the total thermal energy is 5 degrees of freedom. That equals N 5 over 2 KT equals 5 over 2 N KT, and PV equals little n big RT equals big N KT. So we have pressure and volume. So we can say that this equals 5 over 2 PV. Therefore, changing U during any step is 5 over 2 PF VF minus PI VI. Interesting. So U equals 5 over 2 PF VF minus PI VI. Not necessarily the change in pressure times the change in velocity. It's the change in pressure times velocity. So I think I could write this as PF VF minus PI VI, where F stands for the final and I stands for the initial. For instance, during step D, U is negative. All right. Interesting. So for D, the pressure doesn't change, so it just ends up being no change. So basically, it's final, and there's no like the final is the initial. So you think that should equal 0, but it just stays the final. Heat added to the gas during any step is just Q equals change in W minus change in U minus W. See what they're doing. So this is 5 over 2 PF VF minus PI VI. So this equals 5 over 2. So for instance, we use D, let's do B. So for B, you have the final pressure is P2. The final volume is V2 minus the initial pressure is P2 and initial volume is V1. So that's 5 over 2 P2 V2 minus V1. So it's not 0 because they're multiplied together in that way. And that's exactly what they have there. Get it backwards. So right for B. The heat added to the gas during any step is just Q equals change in U minus W. It should be the first law. So again, for step B, Q equals, well, let's U D is 5/2. Final, final pressure is still what it is, P1. Initial volume is V1 minus V2 for negative. And then work, the work for D we have is P1 V2 minus V1. So that ends up being 2/2 times, so either, oh, I see. We need to put them in the same form. P1 V1 minus V2 plus P1 V1 minus V2. So that equals 7/2 P1 V1 minus V2. Seems like my negatives may be off. Look at the total, we just add up everything. We found the interest in the last row by adding up each of the columns and simplifying the result as much as possible. If that should happen, it must be something like the following. During step A, we hold the piston fixed. We heat in, say a flame. During the same step B, during step B, we let the piston out. I'll continue putting heat source at the rate so that maintain constant pressure. During step C, we hold the piston fixed but suck heat out. That's why I'm immersing the whole thing in the ice bath. And during D, we push the piston while sucking heat out so the pressure again remains steady. The net work done on the gas during the whole cycle is negative. In other words, the net work done by the gas is positive. This is as expected because the pressure is higher when the gas is expanding than when it is being compressed. So the pressure is lower when it's being compressed, so the temperature is lower, it does less work. Pressure is lower when it's being compressed, so in D, when it's being compressed, the volume is shrinking. Pressure is lower, so it's cooler. Therefore, the amount of work in this part would be less than that part when pressure is expanding. So we'll count positive work as expanding. So the part of expanding work is bigger. As the work done by the gas is positive, so the work done on the gas is negative. Notice that the net work is just minus the area enclosed by the rectangle cycle in the diagram. the net change. The work equals negative PV, P change in V. It's negative P2 minus P1 times V2 minus V1. So basically you can get work by just simply getting the difference or the change or the value of the width of the axes multiplied by each other, which is just the area of that curve. All right. Pressure times volume gas makes this very convenient. Pressure times volume gas, the work is the area of the square encompassed by the total uh, work and volume. The area ascribed by the total work and volume. That's good to know. The net change in the energy of the gas is zero, as it must be. The state of the gas, as determined by its pressure and volume, is the same at the end of a cycle as it is at the beginning. Therefore, the net heat put into the gas must be minus the net work done, and indeed it is. In summary, this procedure results in a net conversion of heat input into work output. Need to study this one again, but I do want to make sure I get through all the problems. I remember seeing something about stuff. Okay, so we'll keep going. Next problem is 135, 3 problems left. 35 says derive equation 140 from equation 139. So I definitely want to see what they did here. 35. Equation 139 is V T F over 2 equals constant 1.39 and V gamma P equals constant 1. See what we have. starting from 139, V T F over 2. We're going to use the ideal gas law to eliminate T. So PV equals nRT equals big N KT. So they use NKT. So PV over NK equals T. So that means that V equals constant V PV over big N K F over 2 equals constant. And raising both sides of this equation to power 2 over F gives V squared T over N K equals constant times F over 2. So we can say V squared T equals NK constant F over 2. Just up here. This will be V PV F over 2 over NK F over 2. K F over 2 is V PV F over 2. So if I raise everything by 2 over F, we have V 2 over F PV equals NK constant. V over 2 F over F P V 1 plus 2 over F equals NK constant times 2 over F. Good so far. The right hand side of this equation is just some new constant, while the exponent on V is 1 plus 2 over F. So 1 plus 2 over F equals F over F plus 2 over F equals 2 plus F over F, and that's gamma. We have P V gamma equals, right, we just collect all of those into a constant. So this is, to understand how this is just a number, but K is actually, that's units. So A, I don't know what it is exactly. I've used it in one of the previous problems. That was used before. Here's the Boltzmann constant. Oh, here it is. K is 1.3131 times 10 to the negative 23 joules over K. I don't know how they can make that into just a constant. Because technically, it is the Boltzmann constant. It doesn't change. So even if the constant has units, technically it's just another constant with units of the Boltzmann constant. Seems kind of hand wavy to me. So I like the way I did it better. Basically all we have to do, we want to get V gamma P. We use the ideal gas law to get rid of T and put P. Anything that was not P, we just put it on the other side and solve for the exponent and got what we needed. It is simpler. All right, two more problems. 136. In the course of pumping up a bicycle tire, a liter of air at atmospheric pressure is compressed adiabatically to a pressure of 7 atmosphere. So adiabatically means it's so fast that it's fast compared to the speed of sound. Basically, it's air so fast that the air can't respond, so it doesn't compress equally. That's mostly diatomic nitrogen and oxygen. And what is the final volume of the air? From equation 140 derived in the previous problem, we have Tv gamma equals constant. Thus, Tf Vf gamma equals Pi Vi gamma. So we can say Vf gamma equals Pi Vi gamma over Pf. So Vf equals Pi 1 over gamma Vi gamma. We can say Vf equals Pi over Pf 1 over gamma Vi. Pf 1 over gamma. Yep. We put the pressure volume is 1 liter. 7 atmospheres the final pressure, 1 atmosphere is the initial. Saying diatomic nitrogen and oxygen. They're saying it's 5 degrees of freedom. That 1 atmospheric pressure. So in the normal conditions, the vibrational is frozen out, but it seems like they're not applying that. And on the exam, they said that we'll assume everything is working. So In my problem, I would have just used 7 for the degrees of freedom, which would have made that um, 7/9 liter. So we got that. How much work is done compressing the air? Now we actually have to break out an integral. So we have work. Oh, by the way, I should put this equation on the formula sheet. Write this over. Should be sufficient for me to remember. Just think and catch the gamma symbol. Yes, I can't. B gamma P. Right. Now we have this integral to work with. I'm gonna run out negative integral P dv. So we use something more discrete. Just write out what they have. Negative P I V I gamma integral V I V F V negative gamma dv. That makes no sense to me. It says the pressure as a function of volume is P equals constant. Okay, so pressure as a function of volume equals, so we have P V gamma equals constant So PV equals constant divided by V gamma. No, on this one, I think I prefer the way I did it. So, see what I can pull up from when I did this problem. I didn't get the right answer. Right. I'll come back to this one. Now C says if the temperature of the air is initially 300 Kelvin, what is the temperature after compression? And I do believe I got this one. Yes, I did. I was actually surprised at the temperature. So the temperature basically uh, using C for C, P, V gamma equals constant. So PF VF gamma equals PI VI gamma. We want the temperature. So you need to write this equation on the formula sheet. VF TF F over 2 equals VI TI F over 2. think that's it. VF TF F over 2 equals VI TI F over 2. So this is definitely one for the formula sheet. Actually, it's easy enough. We just solve for TF F over 2 equals VI TI F over 2 over VF. So TF equals VI 2 over F TI VF, also 2 over F. And when we plug in all the numbers, we get about 20 Kelvin, which that was a bit much, but that's what it is. Because bike tires don't normally go to 7 atmospheres. Now, last problem, look at this one again. This one, and the last problem, 138. Is since the bubbles, so we have two identical bubbles of gas that form at the bottom of a lake, then rise to the surface. Because the pressure is much lower at the surface than at the bottom, both bubbles expand as they rise. However, bubble A rises very quickly so that no heat is exchanged between it and the water. Meanwhile, bubble B rises slowly, impeded by a tangle of seaweed, so that it always remains in thermal equilibrium with the water, which has the same temperature everywhere. Which of the two bubbles is larger by the time they reach the surface? Explain your full reasoning fully. So let's see what the book says. It says since the bubbles each contain the same number of molecules and each end up at the same pressure, the ideal gas law tells us that whichever one has the highest temperature at the surface also has a larger volume. So they're saying EV equals little n big RT equals big N KT. So V equals N big RT over P equals big N KT over P. Whatever has the highest temperature is value. A and R and K and big N are constants. The pressure as in the pressure will go down. Or just make it bigger either way. The pressure goes down is because it expands and it cools. And one of the bubbles goes fast enough where it doesn't cool. So the pressure stays the same. And the one that goes quickly, which is A, bigger. The one with the higher temperature is the one with the larger energy content by the equipartition theorem. And I believe I have that one. U equals NF 1/2 kT. Larger energy, higher temperature. So the question is, which bubble has more energy at the surface? Since both bubbles expand, they both lose energy as they do work on the surrounding water. Apparently, bubble B absorbs heat to replace this lost energy and thus remains at the initial temperature. Since bubble A does not absorb any heat, its energy drops. So bubble B is the one that does absorb heat and ends up at a higher temperature and thus has a larger volume. Bubble B does has a larger volume, but it's not because it but my reasoning is different than what they have. They're saying, and I guess the key here is when it says that the water has the same temperature everywhere. So the air does work on the water when it expands, thus it cools. The one that goes up slowly absorbs heat, so it's warmer. So bubble B is bigger. All right. Thank y'all for watching. Like, subscribe if you haven't. I'll probably be back later this week to do some more problems, or early next week. You can check my other channel for less involved uh, uh, problems. But I'll be back for some more in-depth problems on this channel either later this week or next week. See y'all next time.